in particular, this week we are going to focus on alternating series. And on Thursday, I'll be giving you guys a review about how to apply the various different tests under different circumstances. So basically, that's on Thursday we'll be doing some kind of overview about what we have done so far, about all different tests we have about series. But today our focus will be on alternating series, because alternating series is another big topic in terms of converging and diverging series. So this is the one very important kind of series that we must master for the final exam, actually. I can guarantee you that there will be at least one question about alternating series, for sure. So there's no doubt about this. So you need to learn this topic very well, actually. Okay, so without any kind of further introduction, so let me begin by introducing what is the alternating series and what is the alternating series test and what it's about in that theorem. So suppose that the condition is the following. If we have a sequence of number is a sequence of number. Actually, I want this to be positive numbers. Such that for one thing, an decreasing. Secondly, an goes to 0. Okay, these are the two conditions that we must for alternating series to meet in order for converging. Is that first of all, the terms has to be decreasing, and secondly, the terms has to decrease to 0. Then the summation negative to the nth power, an goes from 1 to infinity, is converging. Okay, so this is the one part of alternating series test, is that you want the series, if you only look at the positive part of the series, okay, you want this series, the sequence of number an, to be decreasing to 0 in order for this alternating series to be converging there. Okay, so this is one big condition. So both conditions are needed for this to be converging. I'll be giving you guys examples where if one condition is met and the other one is failed, and you can produce example where this is not true, and we'll be seeing that. Okay, this is one part of the theory of the conclusion. Secondly, this is the first conclusion that is converging under these conditions. Secondly, you can estimate the partial sum Sn, the first summation of the first n terms, with the real summation, the real value of the converging series, is given by the difference, is given by an plus 1. Okay. Remember here, an plus 1 only refers to the positive part of the alternating series. If you look at my notation here, forget about the sign, you get the an there. Okay, so that is to say, the first nth partial sum will be estimated by the size of your n plus 1th term, the next term in your first nth term. Okay, so this is the second condition. Okay, so with this theorem, this is the big theorem. This is a theorem that you really want to memorize and have in your mind that for the final exam. Let's see some examples and to understand what's going on here. Okay. Actually, before I do anything, let me draw a cartoonistic like picture what's going on. If we look at, excuse me. Sorry, guys. So let's look at the following way to see why this is true. What does these two conditions actually is doing in order to help us? Suppose that you have a sequence an which is decreasing to 0. Then let's look at a cartoon picture about the nth partial sum, Sn. Okay. Suppose that you start from here. Suppose this is 0, right? Okay. And then for S1, what you do is, for S1, you're adding A1 to it, right? You're basically adding A1 or minus A1. Let me do the following notation here. You're making A1 positive, okay? So what is A1? A1 is probably here, right? So this actually equals to S1, your first nth partial sum, okay? And then what happens to the next term, S2, is that you are going to subtract A2 from A1, because S2 is A1 minus A2 according to the definition of alternating series. The sign has to change. So what is A2? But you see that here is where decreasing is making sense, because if you want this to be decreasing, that means A2 has to be smaller than A1. So you're going back a little bit, but not completely to 0, right? You're going back to probably here. Let's see, this is S2, right? But then for S3, what you do is you're adding A3 to it. But A3 is smaller than A2, so you're not going to completely reach to this point, but somewhere here. That makes sense? And then if you're going back to S4, then S4 is going to be somewhere here. You see that you have a bunch of S2, S4 increasing and a bunch of S1, S3 decreasing, but they are mutually like in this tendency. So in some sense, there will be a limit, which is called S, which is the real value of this alternating series. And this is why it's converging in this sense, because we know from the one theorem in the sequence we mentioned is that if you have a positive increasing or decreasing sequence, you always have a, if they are bounded, then they must have a limit. So you have a bounded increasing sequence S2, S4, S6, and you have a bounded from below decreasing sequence S1, S3, S5, and so on and so on. These two sequence both goes to the same limit, which is called S, and that's the limit of the alternating series. So the picture is roughly the following. You're going back and forth like these. You guys see that why the alternating series is making sense now, because for the partial sums, it's actually just, it's something like this, okay? So this is the kind of the cartoonistic understanding why these two conditions guarantee is converging. Now let's see some examples how to apply these and the examples where they can make the sequence fail actually. So example 1. So let's look at the following sequence. Okay. If we look at this sequence here, my first question is, do you guys believe that this sequence here, the -1 to the n plus 3's term, and let's see, n goes from, let's see, 1 to infinity, okay? It doesn't matter which term this starts, this really begins. But do you guys believe that this is an alternating series, first of all? Okay, so it is alternating series, because for a series to be alternating, all you need is for the signs to change from positive to negative, right? And that's it. And that's actually guaranteed by this part. You have this -1 to the n plus 3 term, which makes the whole thing having alternating signs, just like, yeah. So we understood, so we know this is alternating series. And now let's see if this one is converging. So to test if this one is converging, all we need is to see if these two conditions are met, right? Let's see if let's look at the limit then. So what's the limit when n goes to infinity of n squared over n squared plus 4? So what's the limit of these? Can anyone see that? N squared over n squared plus 4? Is that actually equals to 0? Basically, the reason why we're looking for 0 is because we want the sequence, the an's term, to be going to 0, right? Is this 0?
No, it goes to 1.
Yes, it is 1 actually, which is not 0. So let me change a pen here. This one is kind of hard to read for you guys. So this is actually going to 1, which is not 0. Then this implies that the series diverges. Okay. Quoting a different test. So let me actually make a remark here. This is something I want you guys to really learn in terms of testing series, convergence or divergence, is that you always look at the nth terms limit before you do any kind of other tests. So far you have learned the root test, the ratio test, you have learned about alternating series test, you have learned about the comparison principle, all these fancy tests. But the most fundamental one is something called nth term test. Is in order for a series to be converging, you need the nth term of the series to be going to 0 for sure. If this one fails, your series will definitely diverge. Okay, so remember these. Because the one simple explanation is the following. If the nth term doesn't go to 0, for example, if the nth term goes to 1, for example, that means when n is very large, what's the behavior of the series is that you are basically adding a bunch of 1s together, because the limit is 1. That means all the nth term roughly looks like 1. Not too much, not too small, right? It's nearby 1. So you could see that it's, roughly speaking, adding infinite many 1s together, which definitely blows up. Similarly, if the nth term goes to, let's see, negative 0.1, right? Then that means when n is very large, your an is almost close to be negative 0.1. But when you add them together infinite many times, you get negative infinity, right? So this is one heuristic that's why the nth term has to be 0 in order for it to be converging. But the nth term test is a necessary condition. Only the nth term goes to 0 doesn't guarantee it is converging. Just like the harmonic series, where the harmonic series is given by summation 1 over n. Even though the nth term still goes to 0, but it doesn't converge, right? So, but in this case, in our example here, you see that the nth term actually goes to 1, which is an easy test to see it's diverging. Okay, so let me rephrase what nth term is saying is that if you want to prove converging, nth term test doesn't give you that, even if it's 0. But if you want to prove divergence, if the nth term test gives you something non-zero, like in this case, the nth term goes to 1, this will prove to you that the series is actually diverging there. Okay. Any questions about the nth term test I just made? So let me write it down here. So if limit n goes to 0 is 0, this does not imply convergence. This is 1. But if limit n goes to something non-zero, this implies divergence for sure. Okay. So this is the something I want you guys to really remember. This is very useful criteria in terms of testing series divergence convergence. If the nth term doesn't go to 0, then this automatically already tells you that series is diverging. But if the nth term is still 0, you still need to use other tests to prove that it's converging. This is not enough. So counterexample is the following. Summation 1 over n. This is one very important example I want you guys to remember to illustrate the power of nth term test. Okay, and this is the divergence part. Okay, so in our case, because the nth term actually goes to 1, so that tells you that the series is actually diverging. Okay, that makes sense? This first example here? Okay. Let's see, question. Okay, perfect. So let's look at the second example, which is this one. So let me actually make up the following example. Example 2 is that let me ask you a following question. Is this one converging or diverging based on my So I just mentioned that this is a harmonic series and this one diverges, right? What about this one? Is this one convergent or diverging? 1 over n squared? Anyone knows this?
P series.
P series, and in this case, P equals to
Greater than 1?
bigger than 1, which is 2 in this case. So this one is diverging or converging?
Converging.
Converging, yes. Okay. So this one is converging. Now I'm going to do something, just look closely. I'm going to do the following. So let me actually make this one n start from 2, okay, just to make it more easy to illustrate. Actually, that's fine. Okay, I'm going to do the following. I'm going to make the following series, alternating series, cut by shuffle these two series together. So the first term will be 1 over 1 squared. It's taken from this series. But the second term is coming from this series, which is minus 1. The third term is by adding 1 over 2 squared. And then the fourth term is by minus 1 over 2. And then the next term is by adding 1 over 3 squared. And the next term is by minus 1 over 3. And so on and so forth.
Can you move the paper up, Bo? I can't see what you're writing.
Okay.
Thank you.
Can you see right now?
Yeah.
So you see the point of this construction is that I'm shuffle terms from this sequence, this series, to be the odd terms, 1 squared, 2 squared, 3 squared, and you can see, etc. And the even terms are coming from this sequence from this series with a minus sign in front of it. So 1 over 1, 1 over 2, 1 over 3, but you see the minus sign here. Okay. Do you guys believe that I have constructed an alternating series? Do you think this is an alternating series?
Yes.
Yes. But do you think that this one is converging? First of all, let's look at the nth term. Is the nth term going to 0 for this series or not? So what is the nth term? The nth term is either 1 over n or 1 over n squared, if you look at the absolute value of the nth term. Does that make sense? So if you look at the nth term of the series, of this series, actually definitely goes to 0. It's either the nth term equals to either 1 over n, minus 1 over n, or 1 over n squared. And both of these goes to 0, right? So the nth term definitely goes to 0 as n goes to 0. As n goes to infinity, sorry. So this one passes through the first test, which is an goes to 0, right? An definitely goes to 0. But the problem is that, do you think that the an is actually decreasing to 0? If you look at the series here, is this one decreasing, do you think? So you see that you have 1 over 1, and then minus 1 over 1, and then plus 1 over 4, but then minus 1 over 2, and then plus 1 over 9, then minus 1 over 3. So the an here in this case, in my picture, the following sequence is 1, 1, 1 over 4, 1 over 2, 1 over 9, 1 over 3, 1 over, I think, 16, 1 over 4. You can see that this is definitely not decreasing, right? You can see that there are fluctuations here. You can see that? And this actually non-decreasing property is actually making this one non-converging diverging, because we know that this one is converging, right? This one is converging, so it's finite when you add them together. But this one is diverging. So the summation of all this goes to infinity. So if you look at the nth partial sum, you get some terms coming from the second series, which is finite, but you have terms coming from the first series, which is infinite. So this new series that we just produced is, roughly speaking, this series minus this series. Does that make sense? And the limit of that will be something finite minus infinity, which will be negative infinity. So the conclusion is that this series diverges. Okay.
Bo, off the top of your head, do you know how you would write that series? How you would combine them like that?
You mean like a general form? like
Right.
nth term form.
Right.
Yeah, so roughly speaking, this one is hard to write in one uniform formula, but you can write in the following way: is that the a2n equals to negative 1 over n, and the a2n plus 1 equals to 1 over n squared, I guess. So there are, for generally, you don't really need a series to be written in this form. There's no guarantee a series can always be written in the general form that you have in the textbook, meaning there's a uniform formula for it. But so that also give us some kind of freedom in terms of construction new series out of the new old ones. So you can always combine them and shuffle them and permute the order of the terms in the series to produce new series, actually. That's one very cool fact.
Thank you.
The textbook doesn't mention, actually. Okay.
Thank
you. Yeah, for example, yeah, I mean, what's a general formula if you write the pi in 3 equals 3, 1.14, blah, blah, blah. In terms of series, you have 3 plus 1 over 10 plus 4 over 100, things like these. And there's no general formula for this series, right? I mean, so just like as an example here. I mean, there are plenty of series where you cannot write them in the general formula. Okay. Questions so far? Okay, perfect. So now let me give the third example. So far what I'm trying to mention to you guys is I'll give an example where the nth term doesn't go to 0, so necessarily this one is diverging. In the second example, I'll give you a series which is alternating series, even though the nth term goes to 0, but since it's not decreasing to 0, and this one diverges also. So that means these two conditions for alternating series to be converging are both required. That is, an has to be decreasing, and the an has to go to 0 at the same time. Okay. But let me mention the following remark, which is something that people doesn't see in class or in this class, is that in terms of taking tests, for the purpose of making problems for the test, they rarely ask you guys to verify this condition. They never ask you guys to verify this one's decreasing. In general, the examples that they produce for the exam will automatically be decreasing in some sense. So you don't actually have to verify these for the exam. But you do have to verify this condition on the exam. Does it make sense? So let me remark that has Dr. Chadwick mentioned condition 1 in his examples for alternating series? Do you guys remember that?
Yeah, he did.
But did he actually make examples where he verified the decreasing property of the sequence of the series?
I think he did.
Okay, in that case, then you guys do that. But from my past experience, the problem is that for the final exam, because the lecturers are kind of not uniform in terms of teaching these. So some lecturers I've been working with, they didn't actually mention the decreasing property in the past. So for the final exam, I guess this is something that that you can actually, if the series is obviously decreasing, you don't have to see anything about it. You just need to verify that nth term actually goes to 0. Okay, does it make sense? So let me make the one final example about this part, the part 1 of the theorem. So let's look at the summation of n plus 1, n squared, n cubed plus 1. This should be a very easy one, application of the alternating series test. Let's make n equals to 2 to infinity, okay? So in this case, we see that this is alternating series, and we know that this is n squared in the numerator and n cubed in the denominator. We see here the problem that this is definitely alternating series because the sign here, the -1 to the n+1 term, making it alternating signs. But let's verify the two conditions we had in order for it to be converging. That is this one converging, is this one decreasing, and this one goes to 0. Goes to 0 is kind of easy thing to say because the limit of n squared over n cubed plus 1 definitely goes to 0 as n goes to infinity because, sorry for the notation, because in the numerator you have an n squared term, but in the denominator, the dominating term is n cubed plus 1. So this one is larger than n cubed even, slightly larger, but when n is very large, the numerator is like n squared, but the denominator is like n cubed. So the limit definitely goes to 0. So this condition is checked, is correct. And then if this series is actually decreasing, that's actually where I mentioned about, because to verify this one is decreasing is not very easy. So how do you know that a series like this, an equals to n squared, n cubed plus 1 is decreasing? Let's write out the first few terms, because what is a1 in this case? a1 equals to 1 over 2, right? But what is a2? a2 is 4 over 9, right? So 2 and 8 plus 1, and a3 is like 9 over, this is 27, 28, right? You see that? Roughly speaking, this is like a 4.5 over 9. This is 4 over 9, and things like these, okay? Let me see. Okay, but to verify this one is decreasing, we have to verify that an plus 1 is always larger than an, right? That's the decreasing property that we need to verify. How do we do that? We have to look at the following function. Depends on n, which is given by fn squared n cubed plus 1. And how do you see if a function is decreasing on n? You look at the derivative of fm. If the derivative is always 0, smaller than 0, the function is decreasing, right? So let's look at the derivative of this function. If you compute the derivative of this function, you will see that the derivative of the function is actually given by n times 2 minus n cubed over, in this case, I guess it's going to be 1 plus n cubed squared, right, by the quotient rule here. Okay? So you see that in order for f prime n to be smaller than 0, you want n cubed to be larger than 2, right? So that means you want n to be larger than cube root of 2 in order for this to be smaller than 0. Right? To be larger than 1, actually. So that means whenever n is larger than 1 and start from 2 to infinity, the series here will be decreasing for sure. And this is the proof for it. You look at fn, which is the nth term, the absolute value of the nth term, and look at the derivative of the nth term. Imagine n being a continuous variable. You take the differentiation like n is just x or any ordinary differentiable variable, and you get this expression here. And you verify under which condition will this expression be negative, because in that case, that implies the function is actually decreasing, right? Hence, you know that it's actually a decreasing and going to 0 sequence, so that the alternating series you produced from it will be converging there. That make sense?
Bo, is there ever a case where a function is going to be decreasing, or where it's going to approach 0 but not be decreasing?
That's the one that I've been producing before, right? This is the example I produced to you guys, that you have a series where it's going to 0, but it's not decreasing, right? Let's look at this again. So if you look at the nth term here, yeah, so this one is actually not decreasing, as you can see from the terms I wrote down here.
Okay.
So that's the point of the second example, is that to see Even if the nth term goes to 0, it doesn't necessarily mean that it's converging, because you still need decreasing property to guarantee it's converging. What I'm trying to make here in the remark is that, let me rephrase it in a different way. For our final exam and for our quiz proper, for our just, for taking exams purpose, the only way to prevent alternating series from converging is if the nth term doesn't go to 0. Let me make that clear. You don't, in general, have to worry about the decreasing property. That's what I'm saying. Because for most of examples, actually for all the examples you'll be seeing on the exam and on the textbook about the decreasing property, the series doesn't have to be always decreasing to guarantee convergence. You only need the series to be eventually decreasing to guarantee convergence. And that's why it's really hard to check and verify for general functions, because you can write down a very complicated function where the function is actually increasing at the beginning, but eventually decreasing. And it still will be converging then as an alternating series. So that's why in the test, you will seldom verify the decreasing property of alternating series in general. You only need to verify the nth term goes to 0. Okay, does it make sense to you all?
I do.
Okay, good. Hopefully this clarifies something. If I'm really confusing you guys, actually, I would suggest you actually go to the test bank and look at the past year's exam questions to have a sense what kind of questions are asked for alternating series and what type of alternating series you really have for the final exam. There's no question about the decreasing property. It's all about the nth term goes to 0 or not. Okay. So this is actually the first part of the alternating series test, is tell you under which condition will the series be converging. And there's something very special about alternating series where other series don't have. It's about the estimate for error, which is very important, because if you have an infinite sum, right? Just imagine that no one can really compute it. If you just tell me, give me infinite many numbers, ask me to add them together, right? There's no way you can do it by a human being. The reason why we are interested in infinite summations is only for theoretical purpose. But for application, we always want to use the nth partial sum to approximate our infinite sum, right? You're only going to use finite sum to approximate infinite sums. Then the question is, how good is our finite sum as an approximation then? Luckily, for alternating series, the estimate is very easy, and it's given by the n+1 term as the upper bound for your error. So let me illustrate that. So let's look at the following example. The example is the following. I want to find out the following sum. The -1 to the nth power over n factorial. I want to find the sum. I want to find the approximation of this infinite sum, which is correct to 3 decimal places. Okay. Here's my goal. I have a series, an alternating series. I will verify first that this one is converging. Not only that, I know it's converging, actually I can find an approximation to it that is correct to 3 decimal places. So let's do that. First, let's verify this one actually goes to, is converging then. So let's see first, what is the limit of the nth term? The nth term is exactly 1 over n factorial, which definitely goes to 0, right? This is clear that when n goes to infinity, this fraction will definitely go to 0. This is exponential decay. I mean, there's no, this is really fast decay already. And what about the decreasing property? This is definitely decreasing because n+1 factorial definitely going to be smaller than n factorial, right? You're making the fraction, the denominator larger and larger, so the whole fraction becomes smaller and smaller, right? So based on these two criterion, we know that, hence, the series, the alternating series above, the above alternating series converges. Okay, so we know the conclusion is that it's converging. And then the question is, as we know it's converging, how can we actually find a good approximation? So let me remind you again something even earlier, is that at the beginning of this part, this whole chapter, we learned two very special series, the geometric series and the telescoping series. For those two series, as long as you know it's converging, you actually can find out the numerical value of the infinite sum. There's no need for approximations. But for except those two things, where you can actually find the exact numerical value, then for the remaining part of the chapter, your only possible goal is to find good approximations. And then it comes in this example, alternating series. Because for alternating series, you have a very good theory about how good approximations look based on the expression here. Let me use that. So in this case, we know that we want to find the approximation so that it's correct to 3 decimal place. How do you do that? Make a list of the first few terms and see how good they are. So let's look at S. S equals to n equals to 0. The first term is 1 over 0 factorial is 1. Okay, so this is 0 factorial. Okay, remember this fact, 0 factorial equals to 1. The second term is minus 1. 1 over 1 factorial is still 1, okay, in the denominator, which is kind of weird, but there's a logic reason why this is true for continuity properties of the n factorial. Okay, and the third term is 2 factorial, and the fourth term is 9 factorial, and then you have 1 over 4 factorial. So let's have a sense of what this looks like. This is 1 over 2, this is 1 over 9, this is 1 over 16. So roughly speaking, this is like to the first decimal place. But then if you look at the next term, what is 5 factorial? 5 is already 120. So this is like the second decimal place, right? This term is already in the second decimal place. Let's look at the next term, which is 6 factorial. What is 6 factorial? It's 6 times 120, which is 720. So this is almost close to be third decimal place. What is the next term? The next term is going to be minus, sorry for the sign here, 7 factorial, which almost look like, which equals to 7 times 720 is 5040 already. Okay, so let me write some things like these. So this is 1 minus 1 plus 1 over 2 minus 1 over 6 plus 1 over 24 minus 120. You see that this term corresponds to 5 factorial is already in the second decimal places. And then you have a 6 factorial, which is 720, almost close to be the third decimal places. And then this one is minus 1 over 5040, which is for sure in the third decimal places. Why do I stop here? Why do I stop at this place? It's because by the theorem I wrote down before, look at this one. I know my error is given by, roughly speaking, given by my n plus 1's term. Suppose I want my error to be correct to the third decimal places, that meaning in later words, I want my error to be smaller than 1 over 1,000. That makes sense? So as long as I can find out the very first term in the list, which is smaller than 1 over 1,000, and that is the term I want to stop. So this is actually the n plus 1's term I'm looking for. And everything before it will give me the good approximation up to this error here. Okay, that makes sense? Everything here so far? Any questions? Okay, I will assume that everyone is following here up to this point. Okay, so if that's understood, then we know that S6 minus is the approximation we are looking for. As the error between S6 between S6 and S is bounded by 1/5040. Okay. So this is a typical strategy for you to work with error terms for alternating series, is that you write down the first few terms until you see the next term is within the required bound for error. Does this make sense? Okay. So with that said, that's, yeah, let me actually, let me see some examples, actually, another example. But actually, I don't think there's, yeah, this is really something you have to practice once for yourself. So let me actually give out the questions I want you guys to work on today. The questions I want you guys to work on today is given by the following. So the questions is given by, on the worksheet that's been given out by Dr. Chadwick, you look at 7.7/7.9a. You work on the following problems. You work on 1b, you work on 4, and you work on 5b. Okay, and for 9.8b, you work on 1d, and you work on 2a and b. Okay. And these are the questions I want you guys to submit by Thursday for this week's worksheet. Okay, these 5 questions, actually some part of 5 questions, that's what we are going to work on today, this week actually. If you can finish early, that's much better. So I don't think there's anything really typically hard because I'm choosing it appropriately here. So 1b, number 4, number 5b, and from the second worksheet, you work on 1d, 2a, and 2b. Okay, does that make sense?
Thank you, Bo. Is that all?
Yep, that's all. Actually, I just want to ask you guys, actually, how's the lectures going? Everything's good?
It's been good for me. Like just this last section on 9.8, I've been pretty confused on that myself.
9.8 is on power series, right?
Yeah, power series and like radius of convergence and interval of convergence, I think.
Yeah, that's definitely hard actually. That part is but for the radius convergence is essentially using quotient rule, the quotient rule, right? The ratio test. Sorry, I mean not
okay,
quotient,
right.
but yeah.
Ratio test, right? Okay.
Yeah, ratio test. It's always ratio test, but with yeah, don't forget the absolute value sign when you compute the limit.
Okay, so it'll always just be the ratio test a of n plus 1 over a of n, and the limit as n approaches infinity.
Yes, it's always going to be an plus 1 over an with absolute value when n goes to infinity. And there's something subtle about this, is about the power of the x term. If the x term is only x to the nth power, then what you computed as a limit will be the radius of convergence. But if it's x to the 2n or x to the 3n or x to the 5n, then you have to worry about taking square root or cube root or false root or things like these. So my general suggestion for you is not just looking at the coefficient, but actually looking at everything together, is by looking at an x to whatever it is here, sorry, an plus 1, let's see it's n plus 1 here over an xn. you either look at these, always look at something like these. Don't forget about the x to the nth term here. Because the reason why I've been saying this is, for example, if your series is given by an plus 1 x2n plus 2 over an x to the 2n, if you compute the limit, then this is almost like an plus 1 over an times x squared. And this is nothing but an plus 1 over an times x, right?
Right.
You eventually, how you compute the radius is you want this quantity to be smaller than 1. That
Right.
makes sense?
Yeah.
Right? So that's why this power here actually makes a huge difference. Because if it's just x to the nth power in your series, then there's nothing to worry about because you're just taking a reciprocal of this limit, you find the radius of convergence. Okay. But
Right.
if it's something like x to the 2n as your general term, then you have to take the square root of your reciprocal of this limit, and then that will be your radius convergence. So that's the only subtlety I want to mention for when you evaluate the radius of convergence there. Does this make sense?
Yeah.
Okay, yeah, you need to see a couple examples, and this actually makes a difference here, okay?
Yeah.
The second thing is when you look at, once you find the radius convergence, suppose you want eventually want to find out the interval convergence. First of all, the interval convergence will be symmetric. That meaning it's going to be from minus a to 0, from 0 to a. It's going to be something that looks like this. The only thing is on boundary, you have to be careful because the boundary points may not be symmetric. It may be open, closed, and or closed, open, or closed, closed, or open, open. So you actually have to verify at the boundary points what your series really looks like, and it's going to be alternating series or conditional converging series or absolute convergence series, things like these. You have to actually make a judgment on the base point, not the base point, on the boundary point to see if they are converging there. So,
right. And that would be just plugging the radius of convergence into x, right?
Exactly. Plotting
Okay.
r and minus r into your series and finding if these two series are converging or
Converge,
diverging
right.
there. Yes.
Okay.
Yep.
So,
Yep.
so I'm reading in the textbook, and I'm right past where they talk about how you can differentiate series, and I guess it gets to a point where it says, if you write this down, I'm looking for just a little bit of intuition behind exactly what's going on, but they give the equation e to the x is equal to the sum from 0 to infinity of x to the n over n factorial.
Yep.
And then they give one for the geometric series as well.
Yep.
But I'm not. If you could just kind of give me some intuition on what we're taking it. The limit is n goes to infinity, and that's equal now to a standard one variable function. It just kind of is confusing.
Yeah. So let me see the following. Given that you guys have learned about the geometric the power series right now, let me see that the following. First of all, an to the x to the nth power, n goes from, let's see, from 0 to infinity. Let me first mention that how should you interpret these? The first thing is that a power series, you can vaguely speaking, is a function. Do you guys agree? This is a function, right?
Yeah.
Meaning that if you plot in different value of x, you get a series. If suppose it's converging, then this function will be giving you a value there, right? You give a value of x, it produces a value fx, right? This is a function. My first question is, what's the domain of this function? I guess Dr. Chadwick will never ask you a question like this, is what's the domain of this function? It's actually the question that Carl just asked. Why do you guys compute the radius convergence?
To find the domain?
Yes, that's going to be the domain, because if the radius convergence is like this, let's say it's something like this, then for every value in between these two values, this series is converging, so whenever you're plotting a value there, you get the value of fx. That makes sense, right?
Right.
So this is really a domain of this function here, okay? Now the second part is, if this is the function, if it's converging here, one of the theorem that guarantees is that when you differentiate fx, you just need to differentiate this series term by term, meaning f prime x, you're just given by differentiating everything term by term. That's going to give me n equals to 0 to z, an times n times x to the n minus 1, except for the very first term, which is a0, x to the 0 is a constant. When you differentiate, you get 0. So that's why n start from 1. Okay? So you know how to differentiate. Now let's verify the question that, that Brian asked is, why is this equals to summation 1 over n factorial x to the nth power? Okay? So what is the most important property of e to the x? What happens when you differentiate e to the x? Brian, may I ask you, what happens when you differentiate e to the x?
It's its own derivative.
It's only derivative. So this one, when you differentiate, you get e to the x. Let's look at what's going on here on the right-hand side. Let's write out the first few terms. So this is 1 plus 1 over 1x plus 1 over 2 factorial x squared, things like these, okay? Okay, you can write down this form for yourself. What happens when you differentiate 1? You get 0, right? So this goes to 0. What happens when you differentiate 1 times x? You get 1, right? What happens when you differentiate 1 over 2 factorial times x squared? You get what?
To x.
That will be 2x times 2 factorial, which gives you 1 over 1 factorial times x. That makes sense? Let's write one more term here. So the next term is 3 factorial x cubed. And when you differentiate this term, the 3 comes off because chain rule, and cancel with 3, you get 1 over 2 factorial x squared. Do you see that?
Right. So I guess I see all of this. I'm just wondering how to think about the intuition for it. So I guess if I plug in any value of x into that series, as I take an infinite, if I take n to infinity, it's going to convert. It's going to converge to the value of e to that x.
There are some steps,
right?
There are some skipping of ideas in what you are saying here. So let me say the following. E to the x is a function. E to the x is a very special function which satisfies e to the 0 is 1 and the derivative of itself. So these two properties guarantee the unique function satisfy that is e to the x. Okay? Then on the other side, like I said before, this is also another function, right? It's a power series, and this one, let's call this fx, right? What's the domain of the function? The domain of the function, if you use the ratio test, you will see that the domain of the function is actually from negative infinity to positive infinity. So in this case, a is actually infinity, okay? So this is a function defined also on the whole real line. What is the f0 then? The f0 is given by 1, because when you plug in 0, everything else is just 0, right? f0 is 1. And what is f prime x? You just compute that. F prime x equals to fx. So this is another function which satisfies f0 equals to 1, whose derivative equals to itself. And I just mentioned, these two properties produce only a unique function, the exponential function. And it's for that reason why these two functions are equal to each other. Okay. So one misunderstanding that I guess you guys you'll be having towards the end of the semester is that, suppose you start from fx. Let me say the following. Suppose you start from fx. You guys know how to compute the power series, right? The Taylor expansion of this function, right? This is something like f0 plus f prime 0 over 1 factorial x plus f double prime 0 over 2 factorial x squared. Do you guys remember these? How do you compute the Taylor polynomial? Right? If you extend the computation, you get a power series, right? Let's call this another power series. The question about this equality involving two things. First of all, as a power series, does this one converge, right? If it converges, this one definitely going to converge to a function. Let's call the convergence to a function called gx. Then the second part of the theorem is saying that if this one converges, under what condition will these two functions be equal to each other? You may start from a given function fx, produces Taylor polynomial and Taylor series, which doesn't necessarily converge to itself. That's the key part, which is guaranteed by, which is actually true for some of the most fundamental functions in our world, is like for exponential functions, sine, cosine, logarithm, these kind of functions. The power series you produce from it using the Taylor series actually converge to the original function itself is actually something amazing, actually. It's not something given granted. Does this answer your question, Brian?
Yeah, I think so.
Okay. Yeah, let me know if you have other questions. I mean, and I want to emphasize again that you definitely want to do a lot of exercise on what Carl just mentioned on the finding the radius convergence, find the interval convergence, testing on the boundary points, and then after that you guys be learning the differentiation and integration rules for power series, and after that you'll be learning about the Taylor series and the Taylor theorem, and that's the ultimate goal we are doing for this whole semester, is to understand under which condition you can write fx as a power series, a summation of infinite many polynomial terms together. And that's the end of the semester, I guess, based on our current information. Yeah. Okay. Is there any other questions?
Thank you, Bo.
Yep. So go ahead and work on the worksheets, and let me list them here again, and I'll be sending out the email asking you guys to do this also, and again, upload the work to Canvas Elms, and make sure you finish the work, the web assign. Make sure you do some textbook examples, read the textbook, understanding this part, and let me know if you have any questions through emails. Okay.
I guess I have a very quick question.
Sure,
Sorry to keep you.
Yep.
Just 1 second here.
Yep.
That series that is equal to e to the x.
Mm-hmm.
If I guess we've found that is equal to e to the x, but otherwise we would not be able to find the exact infinite sum. But we know that it I guess I put in quotes approximates, but it approximates exactly e to the x, and using that information we can evaluate the infinite sum of those. That's kind of thinking backwards, but does that make sense?
Let me try to understand your question. I think that the goal, we're not really going to sum up infinite many terms, like I said again. So the reason why we want to write it down is, for one thing, we know it can be written as a power series. That's one theoretical reason why we do this. The second part is, as to what you mentioned, is suppose we really want to find the e to the x. For example, if we want to find the e to the 1, okay? If you want to find this value, e, what is e? You can use the power series to compute it, but then you can use the partial sum to estimate it. And the good thing about this power series expansion is that there's something called the Taylor remainder formula, which tells you how large the error is based on the function's property nearby 1. So to answer your question, yes, in some sense, we definitely can use the power series to do approximations very well, actually. And this only happens for functions which are nice enough, I guess, can be differentiated infinite many times, I guess. Yes.
Thank you. So very, very great answer. Thank you so much.
Yep. Okay, so you guys, I assume that you guys have a wonderful lunch, and let's all get some work done today, and I'll see you guys on Thursday then.
Awesome. Thank you so much, Bo.
See you.
Thanks again.
See you.
Thank you.
Bye, guys.